class. All right, so again, we are looking at the secant slope problem. And next comes the spreadsheet version. So we looked at something similar to this in class the other day. I've added an extra column here that I didn't do the other day called dx, and I'll show in a picture what this means in a minute. But here you can see my x values. I'm starting at the point 1, 1. I'm going back to the point 0, 0, and I'm checking to see what's the slope between these 2 points right there. And then the next line here, the slope of 1.9, that's from the point 1, 1 to the point 0.9, 0.81. And so if I double click on one of these slopes, you can see the 2 points I'm using to get the slope. And so for every slope, I'm always going to the point 1, 1, because I'm curious about what's going on at 1, 1. And it looks like as the x value gets closer and closer and closer to 1, the point I started with up here, the slope is getting closer and closer to what number does it look like there? 2, yeah. And Kelsey asked, can you show us how to find the instantaneous rate of change without having a second point? The answer is within a week. We got a lot of work to do to make that happen, Kelsey. So we will get there though, because it turns out it's slightly different for every function. And I'll show you why here. So yeah, it looks like these numbers are getting closer and closer to 2 there. If we look back at this graph over here, let's blow that up and zoom out just a sec. I had this b down here at 0, 0, where the slope was 1, and then in the spreadsheet, I moved b closer and closer and closer, trying to get to a, but once I get to a, the slope disappears. And if I tried to do that in the spreadsheet, a similar thing's going to happen. So if I get out of there, go back to the spreadsheet, and suppose I put, like, I'm aiming toward 1 here for x, and y is aiming toward 1 there. And if I take my slope formula and fill it down, then I'm going to get an error division by 0, right? That's a problem. So let's look at this algebraically. So the main problem in calculus that we're looking at in this quarter is about instantaneous rate of change. And at the moment, we can't quite get there, and rate of change is synonymous, also known as slope on a graph, right? We have to settle for average rate of change at the moment. And see if we can use a sequence of averages to predict the instantaneous rate of change, the slope at a point. And average rate of change is just slope, okay? And our slope formula, y2 minus y1 over x2 minus x1 requires 2 points. Where instantaneous, we're trying to find slope at a point. Well, how do we change 2 points to 1 point? That's a little tricky. And it's going to take us at least a week to work up to that. Now, remember, y is typically a function of x, so I could rewrite this as f of x2. That's how I calculate y2, minus f of x1, divided by x2 minus x1. And if we pick up the example that we were just looking at, where y is the function x squared, and we were focusing on the point 1, 1. And so let's look at a quick graph there. Switch to green. Let's say there's 1 and 1 there for y. So we know we have a point there. We have a point at 0, 0. 1/2, 1/4 is another point. So this is my parabola squeaking up right there. And we're focusing on this point right there. And then in my previous screen, I was looking at some x value over here. So that would be x, let's call that x2, because this right here is my x1, y1. And then over here, that would be my y2. So if I take this information and plug it in, and this x2 for simplicity, I'm just going to call it x for a moment. So up here, my f of x2 is really just f of x, which is just x squared. So for this particular example, focusing on that point right there, the slope is going to be whatever x value I plug in squared minus the y value, 1 squared, divided by whatever x value I picked here, which I'm just calling x right now, minus the x value 1. So for this function, here's what my slope formula looks like, where I'm varying the second point, but I'm fixed at 1, 1. And that's what I was doing in my spreadsheet here. I was fixed at that point right there and varying the other point on the left side. And I did the same thing over here in this graph. Can I move that up? Yeah, there we go. Where B was down here, and I can see that slope over there. And I was moving that closer. And what we found is when we looked at that sequence of values, the sequence of slopes for each different x value I picked getting closer to 1, I found that the slope was getting closer to 2. So I'm just going to write that in my notes here. So this is my slope formula right here. And what we noticed in the table and in the graph is that as x gets closer to 1, it seems that m gets closer to 2. And somebody, I think it was Cole, asked the other day, well, how do we identify that number it's getting closer to? And we're going to have to accumulate a bag of mathematical tricks to help figure that out. At the moment, the only trick we have is looking at a table of numbers. Okay? And that can be done with a regular calculator or a spreadsheet or a graphical tool like Desmos or GeoGebra. Okay? This idea of letting one variable move toward one number and watching what the other variable does, this idea is called a limit in mathematics. And so I just want to talk more about limits. So we need to figure out how to deal with these limits right here. Now, one thing I just want to note is that this right here, this slope formula I've created based on this situation, this is a whole new function. Okay? It is a slope function related to the point 1, 1 on this particular quadratic graph, this particular parabola. And we could graph it to see what it looks like just for fun. Right? This, if I looked at that all on its own, suppose I said, hey, let's check out the function g of x equals x squared minus 1 over x minus 1. You studied functions like this in college algebra. This is a rational function, right? Does anybody remember how to determine the domain of a rational function? Domain is any x value you can plug in. What x values can I plug in here? What x values can't I plug in? What does this graph look like? Any takers on the domain? We got a couple answers. Every real number and then x equals 0. Okay, so let's check that out. All real numbers except x equals 1. Excellent, lots of good answers there. So the key with finding a domain is generally you can plug in any number you want unless something happens like you end up with a 0 in the denominator or you try to take the square root of a negative number. Those are the two biggest problems we run across. And I do have a denominator here, and if x minus 1 happened to equal 0, I would have a 0 on the bottom, and this function would not have an answer. And if I solve that, that gives me x equals 1. And I knew on the previous page that putting these 2 points on top of each other was a problem, because I'd get 1 minus 1 over 1 minus 1, which is 0 over 0, which does not exist at the moment. So, oops, wrong button, this one right here. So what happens is with this function right here, yeah, any other number is okay. I can plug in 0 here, right? So if I let x equal 0, then I get 0 squared minus 1 over 0 minus 1, which is negative 1 over negative 1, which is just 1. Okay? So I just calculated g of 0 is 1. So 0 is okay. The only number that is a problem here is if I try to plug in 1. That's trouble. So the domain is all real numbers but 1. If I put that in interval notation, it would look like this. Negative infinity all the way up to the edge of 1, union 1 all the way to the right forever. So that would be the domain right there. And if I graph this thing, what I'd find is there'd be lots of points, except there wouldn't be a point where x equals 1. There'd be this little hole in the graph there. So we need to figure out, like, what about that hole? So let's take a look at that. With the definition of a limit, because I'm reading someone's note, by the way, because with all of our previous calculations, we have never gotten a whole number as an answer. It is not possible to actually reach the number we are approaching. Good question, Kelsey. Sometimes you can reach the number you're approaching. Sometimes you can just get as close as you ever want forever. Okay, so if somebody says, I need you to get to within a millionth of the answer, we could say, yeah, it's right here. If somebody says, no, you gotta get closer, get within a billionth of the answer. I can get as close as you ever want me to. So a limit is kind of a dare. You tell me how close to get, I show you how to get that close, okay? Again, I'll define more carefully what a limit means, but for now, sometimes we can actually get to that number and sometimes we can't. And so we'll get there here. So let's look at a graph of this function for a sec, and then I'll write down some notation about limits. Let's go to GeoGebra. Give me a new one. Start. All right, so I'm going to enter a new function. I don't have to give it a name like g of x, but I'm going to. And this is a fraction. And let's see, what do I have? X squared minus 1 over x minus 1. And it draws this graph for me, and it's showing some points here. And interesting, it shows intercept, that's cool. Intercept, that's cool. And then it gives me this point right here, and it says that's an extremum. Now we'll talk more about extremum later in the course, but interesting that it's 1.000004, 2.0000. That's pretty close to 1, 2. I can, since I named this thing g of x, I can do things like say, hey, what is g of 0? It says it's 1. What is g of 1/2? It is 1.5. What's g of 0.9? It's 1.9. But if I say, hey, what is g of 1? It says, huh? I can't do that. It does not compute. You're dividing by 0. That's a problem. So there is a little hole at the point 1, 2. That doesn't exist there. So let's do a little bit of algebra here. So reaching way back in your mathematical history, in a class like Algebra 2 or Intermediate Algebra, you might have been given an expression like x squared minus 1 divided by x minus 1, and you might have been asked to simplify this. Let's see, can you make a table in GeoGebra similar to Desmos? The answer is yes, you can do tables in GeoGebra pretty similar to Desmos. GeoGebra has a spreadsheet view, but I'm not going to go over that in class today because I like regular spreadsheets better, but it is possible. Anybody remember how to simplify something like this back from their algebra past? How do I check if this simplifies? There's 2 ways to do it, at least. Make the numerator a binomial. Yeah, see if the numerator factors. And hopefully you recognize that as the difference of 2 squares. And so the numerator factors as x minus 1 times x plus 1 divided by x minus 1. What can I do next? Simplify. Okay, what do you mean by simplify? Simplify in math, unfortunately, means a lot of different things. Taking out. Okay, so taking out, in this case, means I have a factor of x minus 1 on the top. I have a factor of x minus 1 on the bottom. A number divided by itself is 1. 1 times x plus 1 is x plus 1. Now, there's a catch here that you may have talked about in your Algebra 2 class or in your college algebra class. This first expression at the top is only defined if x is less than 1 or x is greater than 1. It is not defined if x is 1, because if we try to put x equals 1 in here, we get 0 over 0. So if I'm going to keep this equal sign here, these two are only equal. So this thing up here is equal to this thing right here, only if I maintain those x values. However, I could cheat here and plug in x equals 1. And if I do that, I get 1 plus 1 equals 2, which happened to be the number that the table was leading toward. So sometimes we can do a little bit of algebra jiggery-pokery and take something that was undefined initially, right? Initially, when x is equal to 1, we got 0 over 0 for that. But now I was able to algebraically manipulate it and say, oh, if x equals 1, it's really 2. So here's the language and some notation we use related to that. So we just found the limit of x squared minus 1 over x minus 1 is 2 as x approaches 1. Okay. We let x get closer to 1, and it looked like it was that fraction was heading toward 2. Now, we, just a moment ago, only did it with numbers less than 1, and so I'll get to that in a moment. However, in my spreadsheet over here, I actually have another tab where I did it on the other side. So here I have 1, 1, but now I'm picking points like 2, 4, 1.1, 1.01, 1.001. So now I'm picking numbers on the right side. And I'm getting toward 2 from above there. Okay. So just to see that over here, the point of interest here is the point 1, 1. So oops, no, 1, 2, I lied, right there. And if we move along this curve toward that point, as x approaches 1 from the left side, y is approaching 2 from below. So back here, all these x values right here are less than 1, but getting closer to 1. And all of the slopes are less than 2, but getting closer to 2. If I look on the other side, as x approaches 1 from the right side, okay, so all of these numbers here are greater than 1, but as I move down the list, they're getting closer to 1. The y values are getting closer to 2, but they're always above 2. And we can see that on the graph here too. As we pick a point on the right here and we move that point toward this one right here, as x gets closer to 1 from the right side, y gets closer to 2 from above. And that is an important distinction, and we'll work on that over the next week. Literally. So back here. The abbreviation of this statement looks like this. For limit, we write LIM. As x approaches 1, underneath LIM, we write x arrow 1. The of this thing right here is just written next to it. So next to this limit, I write the fraction x squared minus 1 over x minus 1, and then that equals 2. So again, this red thing is read, R-E-A-D, in this blue text right here. The limit of this function right here is 2 as x approaches 1. Sometimes we can read it like in this direction there. So I could also say the limit as x approaches 1 of x squared minus 1 over x minus 1 is 2. Okay. Now I can't plug in 1, right? That was a problem. So I'm just going to write this down again. Oops, this will be right here. If I write it down again, usually when I see a limit like this, the first thing I do is cheat. What do I mean by cheat? To cheat means to plug in the number. Plug in x equals 1. The reason that's cheating is the language here says to approach. Okay, approach doesn't mean go and grab it. Okay, it means to get closer to. Doesn't mean to get there. So that's the catch here. Approaching means get closer, but don't touch. So touching means plugging in, and that's technically cheating with a limit, but it's a good place to start. So if I cheat, I just plug in that 1 into that expression and see what happens. And I get 0 over 0. Now, 0 over 0 is actually different than like 3 over 0, okay? 3 over 0 definitely does not exist. Sometimes it's said to be undefined, and I'll explain why. 0 over 0 also does not exist, but there's another mathematical word we use for that. It's called indeterminate. I'm just going to play a quick game with you about why I say this one's undefined, but that one's indeterminate. So new page, 0 over 0 versus 3 over 0. Let's see, I got another note. Yeah, well, I'm going to do two things in class, Kelsey. I'm going to explain the theory and I'm going to do some problems. So we'll do some more problems in a minute. But I got to explain this theory, otherwise you're not going to get the ideas later. So 0 over 0. So every division problem is related to a multiplication problem. So consider, for example, 6 over 2. We think 6 over 2 is equal to 3 because 2 times 3 equals 6. So if each of these is going to have an answer, then that means I should be able to rewrite it as multiplication. So with 0 over 0, this relates as taking this 0 times the question mark equals 0. And the catch here is any number works here. Okay, so 0 times 1 is 0. 0 times 2 is 0. 0 times pi is 0. And that's a problem. Which is the better answer? I could even do 0 times 0 is 0. Over on this side over here, if I say 0 times what equals 3, I can't find a number to multiply to get 3 because anything times 0 is 0, not 3. So this one is called undefined because there is no such number to find that works here. Oops. This one is indeterminate because many numbers work and I can't determine which is the best one. Determinate. What we say often instead is both of these just do not exist, which is kind of a generic response there. Now, oops, over here. So limits in general, there's a couple of things that happens with them. Either a limit exists or it does not. So limits exist or do not exist. So an easy limit would be the limit as x approaches 3 of 2x plus 1. If we look at the graph of 2x plus 1 near x equals 3, we're going to see that we're going to find a y value of 7 there. And I can just plug in the 3 and cheat. Right? So I can look at the graph to see, hey, it looks like about 7, or I can just plug in 3 and cheat and get the 7. So that limit exists. Now, sometimes limits don't exist. So for example, the limit as x goes to 0 of 1 over x, this one does not exist. The limit as x equals 0 of 1 over x squared, that one does not exist either, but it's different. And so let's compare these two right here in a graph. Let's clear some stuff here. I want to look at 1 over x. So you may remember this graph back from your algebra days. This has asymptotes vertically here at x equals 0 and horizontally at y equals 0 there. And if I take a point on this graph right here, so suppose I take a slider, point on there. As I take this point and I move it, as the x value gets closer to 0, as I move it this way, the y value is going to get bigger and bigger and bigger. Right? It's going to keep climbing and climbing and climbing. What happens if I try to get it to 0? Right? That's a problem, because if I say, hey, what's g of 0? It's going to say it's infinity. Well, that's weird. Is it really infinity? Well, if I'm on the right side here, I'm heading toward positive infinity. But what if that point was on the left side here as x gets to 0? So for example, g of negative 0.1, g of negative 0.001. Here I'm going to negative infinity. So if I write that down with notation, so I'm focusing on this one right here, the limit as x goes to 1, but if I just stay on the right side, I put a little plus right there, so that means on the right of 1, of 1 over x, I get the numbers are increasing without bound. That's what the infinity means there. They're increasing forever, is what the infinity tells me. Now, is infinity a number? The answer is no. So this is a fancy way of saying it does not exist, but in a particular way. If I look at the limit as x heads toward 1, but I put a little dash and negative right there, that means on the left side of 1 for 1 over x. Then I'm actually heading toward negative infinity. And negative infinity is a different direction than positive infinity. This is interpreted as decreasing without bound. Which is a more specific way of saying, hey, it does not exist. There is no number that this is going to. It's just going up and up and up and up forever and ever and ever. Now, if I compare that to the other function, so by the way, the right doesn't match the left. So when I say what's the limit as x goes to 1, and I don't refer to the right or left of 1 over x, I can't say it's infinity and I can't say it's negative infinity because it depends on which side you are. So I would have to answer does not exist here because the left and right do not match. So with the other function I was looking at, 1 over x squared, let's take a look at its graph to see what happens. So I'm just going to put a square in the bottom here. Notice now, it doesn't matter which side I'm on of x equals 0, the y values are heading up on each side. So over here, again, I have some negative values. X equals negative 1, I get 100. X equals negative 0.001, I get 1,000,000. That doesn't look right. Oh, it's squaring. Yeah, so that is right. If I look on the right side, like I plug in a number close to 0, but on the right, I'm still going to get positive numbers also. So it doesn't matter whether I'm on the right or the left, the same thing happens, it's heading toward infinity. And so the point here is a limit is you have to look at the left side and the right side to make sure they match. And experience counts for a lot on these. So we're going to do a lot of examples over the next couple of days. So as x heads to 0 on the right side, it's increasing forever. And that's what the infinity really means here. If I look at the limit as x approaches 0 on the left side, so that's what that means there, I still get increasing forever. So that means since these guys match, I can say the two-sided limit as x approaches 0, and I don't put a plus or minus, means it could be either. I can still put an infinity here. Now here's a question though. Does this limit exist? I mentioned before, either a limit exists or it does not exist. Does this limit exist? No takers. Evan says yes. Okay, anyone else? So here's the deal. To exist means the answer is a number. Is infinity a number? The answer is no, so this limit does not exist. Since infinity is not a number. To exist means it came to a number. So those are the two options. Either the limit comes to a number that we can identify, or it doesn't go to a number. And infinity is not a number. So since infinity is not a number. I'm in class right now, just give me a few minutes. All right, so let's take a look at a couple of homework questions. Yeah, it's not really a philosophical question. It's just, what does exist mean? So I exist. I'm going to stop sharing for a second. And let's switch to speaker view. So I have two fingers right there. So the number 2 exists because I can identify 2 fingers. So 2 exists. We think the number pi exists because we can draw circles, and pi is related to the circumference of a circle. We think the square root of 2 exists because on a right triangle with sides of 1 each, the diagonal is the square root of 2. However, infinity doesn't exist because it means do something forever, and we can't do anything forever. All right, so existence there, it's kind of philosophical, but forever doesn't exist as far as we know, being humans. Pi it's got a decimal that goes on forever, but it is a very specific number on the number line. So pi does exist. It's just the way we write it as a decimal is tough. So if a circle exists, then pi exists. So that's the other question. Does a circle really exist? Are there perfect circles in reality? I don't know. All right, homework time. I'm going to pick an interesting problem from the homework. Oh, I got another chat. Why does the chat keep disappearing? And how did student view? Oh, I was in student view. There's the chat. Let's see, in a way, but it can be visualized in a way. So can infinity be visualized? I mean, I can draw an arrow that says go right forever, but we can't actually do it. Can I draw a perfect circle? That's questionable. Can a computer draw a perfect circle? That's questionable too. So yeah, now we're getting into some very philosophical stuff. All right, homework 2, limit of a function. So let's play around here for a few minutes. All right, so we've looked at problems like this before. You have this expression here. You're to plug in the x values and see what happens. So this would be on the left side of the x value, plug in the x values on the right, and see if they agree on where they're going. So that's similar to a problem I did today in class. That's also similar. That one is similar. That one is similar. There's no algebraic trick on this one, so that might be a good one to look at here. That one also. Sine of x over 2x, or sine of 2x over x. Yeah, let's take a look at that one right there. Okay, so sine of 2x over x, and I want the limit as x goes to 0. And nicely, they show me the graph here. So with all your homework, you should definitely write things on paper. Which number was this one? Number 6. So homework 2.2, whoa, my pen is freaking out. Number 6 said to find the limit as x approaches 0 of the sine of 2x over x. And they gave me a graph of it, but I'm just going to put the graph in GeoGebra. Let's get a new GeoGebra up here. And I like using function notation, but it's optional because it makes it easy for me to plug in x values. So sine, 2x over x. And I'm interested at x equals 0. And if I try to plug in 0, right, if I try to cheat, the computer says, huh? You can't plug in 0 because you get 0 over 0 there. But clearly the graph looks like it's approaching 2. And I can zoom in there and say, man, that looks like 2. I could check by plugging in some numbers. Like what happens if I plug in, let's go over here, f of 0.001. Hey, that's pretty close to 2, but just a little underneath. Let's go on the other side. What is f of negative 0.001? And the computer says, yeah, that's pretty close to 2. And if I put more zeros in there, it gets closer and closer to 2. And all of a sudden says, hey, yeah, let's just call it 2. Now, it isn't actually 2 there. The computer just ran out of the ability to calculate. Okay? So I can play around with numbers by plugging in my graphing calculator. I was given a graph for this one, and so I can kind of see it looks like 2 there. And so I'm just going to say, yeah, it looks like 2 on each side. All right, so we are about out of time for fun with math. We are going to play more with these questions. If while you're doing your homework, you're stuck and the video is not helping, hit that message your instructor button, and then I can look at what you did and write back to you. You'll know I wrote back when the mail icon in the upper right over here says you have mail. All right, let me see. Any questions before we part? Otherwise, I will see you Monday or through questions online. All right, take care. You're welcome.